we will practice integrating to prepare for our first exam. Here is our first example. This, if we look at it, we see partial fractions. What we see is a single linear term here, and we have, this is a repeated irreducible quadratic, okay? So if I think about this, the form is going to be, well, this is our integrand, and this will be a over x plus bx plus c over the irreducible quadratic, and then one more term, which will be, let's see, dx plus e over the irreducible quadratic squared. Okay, now this looks like it's going to be a ton of work because we have 1, 2, 3, 4, 5 unknowns. But you will see it's not too terribly bad. So what I want to do here, as we do with partial fractions, is we get a common denominator and add. In this case, the common denominator is here. This term will be an a x squared plus 1 squared. Now this term, we have bx plus c. We need 1x and 1x squared plus 1. And then this term, all we need is an x multiplied. So you have plus e times x. Okay, all over this x times x squared plus 1 squared. So I may here, maybe I will continue with my black. I equate the numerators. This is x to the 4th plus 1. And this will equal, well, we have an a. Now if I multiply, I'm going to have to multiply all of this out. I have an x to the 4th plus, I have 2x squared plus 1, okay? Then I have, oh goodness, I will do this in 2 steps actually because I have a lot going on here. Bx squared plus cx times x squared plus 1. I haven't fully multiplied this term out because you see I have 3 things multiplied together, but I distributed the x here and the x here. So now I have bx squared plus cx times this, and then my final piece I can multiply out. Okay, now one more step. I will go ahead and distribute the a here. We have a x to the 4th plus 2a x squared plus a. Here, let's see what I have. Well, we have bx to the 4th plus, we have bx squared plus, we have cx cubed plus cx. And finally, dx squared plus ex. Okay, this looks long. However, let us come on this side, and I'm going to group everything because this is going to all of a sudden make my life easier. Typically, if we had 5 unknowns, that would be quite hard to solve for, but in this case, as I mentioned, not too bad. So what do I want to group? This is generally what we do with partial fractions. You see, I have an x to the 4th plus 1, and this will equal, well, I'm going to have an x to the 4th times, and then a bunch of stuff. So let's find them. My x to the 4th is here and here. This is going to be a plus b. Then I have the next power is a cubed. What are my coefficients? I have cx cubed, c, okay. And then I should have an x squared with a bunch of terms. My x squared, I have a 2a I have a B, I have a D. Okay, so it's going to be 2A plus B plus D. This black is dying. 2A plus B plus D. And finally, oh no, there's two more terms actually. I have an X with here. I have an E. I have a C. That's it. Okay, E plus C. E plus C. And finally, the only thing I have not underlined is there's a coefficient of 1 and then times A. Okay, now this does lead to 5 equations and 5 unknowns. However, it's very nice because if you look at the left-hand side, there's so many things that are 0. This coefficient 0, this coefficient 0, and this coefficient 0. So immediately, what do we get out of this? Let's equate the coefficient, in front of x cubed. We get that c is 0, right? There's one of them. And then let's equate the coefficient in front of the, let's say x. Then we get e plus c equals 0. So combining, we get that e is 0. We know 2 of them already, right? This one, 0. This one, 0. Okay, let's keep going. Maybe I'll box them. Here, here. Whatever one is kind of easy to begin with, we can equate the coefficient in front of 1. We get that a is 1. So which have I used so far? Just to make it clear, I've used this, I've used this one, and I've used this one. And there are 2 more equations that come out of this, but you see I've already determined 3 of my coefficients, and I only have 2 left I need to worry about. Okay, this is very nice. So I still have, now I will write the remaining 2 here. I have a plus b needs to equal the coefficient in front of x to the 4th. This is 1. Then I have this longer one that says 2a plus b plus d would equal, let's see, the coefficient in front of x squared, which is 0. We know a, we can put it into this first equation, and we get this first equation. We have 1 plus b equals 1. Okay, b is also 0. Okay, b is 0. I'll put that here. I'll outline it in red. Okay, so this one is now 0. You see how beautiful this is? As complicated as it looked from this partial fraction decomposition, we are getting zeros for many of the coefficients. Okay, the last equation, well, I can solve for d because I know a and I know b. So let's write that here. I know that 2 times 1 plus 0 plus d equals 0, right? Therefore, d is -2. Okay. We have found d. This one is -2. Okay, so let me write here what this integral is, then I will erase and we will finish calculating. So if we look at these coefficients we have calculated so far, this is equal to the integral. It's 1 over x plus, this term is entirely 0, and then we have, oh, well, it's going to be a minus 2x over x squared plus 1 squared dx. Like this, okay? This integral is 2 terms, which we will do now. this is the sum of two terms. We can write it as the sum of two integrals. Like this. Now, perhaps I will come to the side and work with this integral. This one is ln absolute value of x. It cannot be more straightforward than this. Let's work on the other one over here. So this is a little side work, and then I will have the second integral, and we can write our full answer. This is substitution, where u is x squared plus 1 when we find du 2x dx. Now, we have exactly du. We have 2x dx. Exactly. Okay, perfect. This becomes an integral u to the minus 2 du. And this I'll put in a little box. When we integrate, we add a power, divide by the higher power, plus c. Or this is a negative 1 over u. Maybe I will write it that way as I go back to x. Negative 1 over, and then the last step is composition, plus c. Okay. All of this is the calculation of this second integral. Well, now that I have that calculated, I can just finish the problem here. This is ln, as I mentioned, absolute value of x. And then we have minus, well, this integral. This integral is negative already, so this becomes a plus. We have 1 over x squared plus 1 plus c. The neat thing is, as I mentioned, this partial fractions looked complicated when we started. We had 5 constants, but you can see it's really not too bad of an integral once we worked it all out. If you look at this problem, you see the integrand looks very similar to what was one term in the partial fractions problem that we just did. But here, it looks like a definite integral until you realize the improper integral. Okay, so what even is this? Well, we know by definition this is a limit. Let's say as a goes to 2 is going to 2 on this side. The integral from a to 5 x over x squared minus 4 squared dx. So we have this definite integral from a to 5, then we take a limit as a goes to 2 on the right. Okay, well, this is substitution. This part is very similar to the last, except that we have a definite integral with substitution, but my u is x squared minus 4 du 2x dx. So we don't have exactly du. We have x dx, which is 1/2 du. Okay, so far so good. Now, I always personally change my bounds to u bounds. When x equals the lower limit, u is a squared minus 4. When x is the upper limit of integration, u is, well, 5 squared minus 4, which is 25 minus 4, 21. Okay, wonderful. Now, let's continue. Maybe all of this I will put in a box. We have, this is equal to a limit as a goes to 2 of the integral. Now, my integral is fully with respect to u. Well, my lower limit is a squared minus 4. My upper limit is 21. Then I have, just like in the last problem, I have a u to the minus 2, but I have a 1/2 du because of my multiplier. Now I will integrate. Now, every single time, and this is quite important with improper integrals, every single time you write limit until the very last step where you evaluate the limit. Okay, so let's see, I have a 1/2, and then I add a power, divide by the higher power, which amounts to like this. We would add a power u to the -1 over -1. Well, here's the negative, and then the -1 power is a u in the denominator. We did this integral in the last one, and we evaluate this between a squared minus 4 and 21. Okay, so far so good. Now I am still not taking a limit yet. I need to evaluate. So this is a limit as a goes to 2 on this side of, this is a 1/2 or 1 over 2, and then the upper limit times 21 minus, a minus is going to be plus 1 over 2 a squared minus 4. Then we take a limit as a goes to 2. Here comes the limit. Okay, wonderful. This is negative 1 over 42. This is a number. There is no a. Here's the a. Okay. What's happening? Well, as a goes to 2, this quantity, a squared minus 4, is going to 0. So we have a numerator 1 fixed. The denominator is shrinking to 0. So this fraction is going to infinity. What that means is that this limit does not exist because it's infinite, and the improper integral diverges. Okay, you could say that this limit, you could say equals infinity if you wanted to, or you could write d and e. Either way you think about it, the limit, or the improper integral, I should say, diverges because this limit does not exist as a finite number. There's one more integral to practice, although we are practicing, this integral involves integrating power series. So this question is a little bit different than the last two, but it is also quite important. Well, we want to find a Maclaurin series, or the Maclaurin series, I should say, for this indefinite integral. How are we going to go about this? Well, the first thing we will use is the Maclaurin series for e to the x, and we can compose, multiply, and then integrate. And this is the strategy. Okay, so the first thing is here, we use this. If e to the x is this sum, x to the k over k factorial, which it is, as we've discussed, we know e to the minus x cubed, so e to the minus x cubed equals, well, I'll write it in summation notation first. We just put in minus x cubed for x. This is composition, okay? But you see, I'm going to have to integrate, and I'm going to be multiplying through by a power of x, so I don't want to leave my expression like this. This is a sum. This would be a minus 1 to the k, x to the 3k over k factorial. Another way you can approach this, so you can choose if you want to use summation notation, or for instance here, writing out the terms. If we wrote out the terms here, we would go about it the same way of composing. The first term is 1, and then we have minus x cubed, and then we would have a plus, we would have x cubed squared, which is an x to the 6th, and then we would have a minus x cubed, which is x to the 9th, over 3 factorial, and the next term, for example, we would have x cubed to the 4th, which is x to the 12th. This would be over 4 factorial, like this. The next one would be negative. Okay. This is how, if you want to work with this to go to here, if you prefer that to summation notation. Okay. Now, so maybe I will put dots here, because this is two different ways to approach the problem, summation notation or listing terms You only need to do one. I will show both so that students that use both sides, or whichever way you do it, you see the answer up here. Okay, now I take this power series, multiply through by x. So x e to the minus x cubed. Okay, in summation notation, this is quite simple. All it does is shift the power up by 1 because I'm adding one more power. So I have minus 1 to the k. I have x to the 3k plus 1, and then this remains the same, okay? All I've done here is I shift the power up by 1 because I've multiplied through by an x. What it does on this side, if you are a writing out of terms type person, this becomes an x. This is minus x to the 4th. This is plus x to the 7th over 2 factorial minus x to the 10th over 3 factorial plus x to the 13th over 4 factorial minus, and we'll continue. You see I have 5 terms. It's quite plenty here. Okay, now we have a power series for the integrand, right? We have built it by composing, multiplying by a power. Final thing to do is to integrate. Okay, here we go. If I integrate, don't forget the plus c. This is true every time you have an indefinite integral, but also with power series. Okay, then these are polynomials of x. We are integrating with respect to x. Don't let the k's intimidate you. This part remains. I integrate x by, I add a power, divide by the higher power. Okay. This is one possible answer. This is a Maclaurin series. You see it's centered at 0. By looking at it, this is the Maclaurin series for this indefinite integral. Now, let us also list some terms. As I mentioned, you can, maybe your answers are entirely over here. Maybe they're entirely over here. It's up to you with your preference, how you like to write things. So again, we have our constant, and then all of these, it's polynomial terms. So we add a power, divide by the higher power. Here we're going to have an x to the 8th. There's going to be a 2 factorial, divide by the 8, right? Add a power, divide by the higher power. Add a power, 11th, divide by the higher power. But don't forget, there's a 3 factorial here. And then the final one that I will write, this would be 1, 2, 3, 4, 5 terms. Of course, the plus c is also a term, but not that I had to do much work for. So here, the last one, I would have an x to the 14th over 14, and then don't forget the 4 factorial times, and then the next one would be negative, and this pattern would continue, okay? So this is another potential answer. For integrating this function using power series.